Try this one more time. Okay. So I'm definitely not the first time you've heard the word vector before, correct? No. Yeah, you definitely heard vector. You definitely hear it in physics. You definitely hear it in things like that. In math, we really only focus on the math behind the vector, like kind of looking at this, all of the things that I would think that I would need to say about vectors. To solve the problems that we need to solve in math, I don't really need to say any of those things. So we'll leave that to the Mr. Herbs and the Mr. Herb. I always call him Mr. Herb. There was a Mrs. Herb at Clear Run, and I always picture Ziegler, and I think of his first name, and I call him Mr. Herb. Mr. Ziegler, we'll leave that to the Mr. Zieglers and the Mr. Bittmans of the world to get into the finer details of what vectors are. But they do show up in math. They are a really important word in one type of math called linear algebra. But in the same way as what I just said there, it's really just the math that's important in math. It's none of the stuff that we talk about in physics. So with that being said, here you're going to see that when we talk about vector valued functions, we really are almost doing the exact same thing as parametric equations. The differences are really stuff that, again, is saved for other things, not for what we're doing with them. So we were talking about parametric equations, and parametric equations are two separate equations. You have an x of t and a y of t. You can stick those two equations together inside of a vector and call that a function. So this is Jean's work, so she uses a lot of f's and g's, where Mr. Bean uses the x's and y's. But this is the same thing as taking your x of t, which is what we had with our parametric equation, and our y of t, sticking them next to each other with a comma, and then putting some, I don't know what you would call them. They're like greater than, less than sign looking brackets around them. And that, for what we need to know in the math part of it, is a vector. So basically, it's a parametric equation where we've put the two equations together in some sort of brackets. We often refer to, and I think I've used this word when we were doing the very introductory thing, we refer to the individual functions, the x of t and the y of t, or the f of t and g of t, whichever letters we use, as component functions. So when I was showing you the intro with the particle motion, I was referring to it as an x component and a y component. Same sort of idea there. So when we have these multi-dimensional things, whether it's a parametric equation or a vector, then the individual pieces are called components. The difference between some of the differences between a parametric equation and a vector valued function, if you think about some of the things you know about vectors, we're usually thinking about a magnitude and a direction. So a vector is usually thought of as some sort of line with an arrow on it, where the length of that line is the magnitude of your vector, and the direction that it's going in is the direction part of it. So this isn't really a different way of thinking about it than parametric equations, but if you plugged t values in, you would get the value of the vector at that given time. That vector would be a line starting at the origin and going out towards that coordinate pair. But that's just a little bit extra than what we did when we were graphing parametric equations. Parametric equations said, well, when you put a value in for t, you got the coordinates of your point. A vector valued function is basically the same thing, except we have a vector pointing to that point. The whole idea behind that is it's just whatever context you're working in, but the math makes it a little bit different, but the math is always the same. You basically plug t in and you get a coordinate pair. If it's a parametric equation, it's a dot on your line. If it's a vector value function, it's a vector pointing to that dot on that line. So really, there aren't too many differences. So it's almost like we've got two topics in one. So much so that when you look at this first example, there's like absolutely nothing to do other than put the t back in that somehow disappeared. Express the parametric equations x equals 2 cosine t, y equals t plus sine t as a vector value function. It's literally just putting them in the brackets. Here I'm thinking of a dot moving on a line. Here I'm thinking of an arrow starting at the origin and pointing to the dot that's moving on that line. I think it's harder to explain things that there's very little difference between than it is to explain something complicated. But yeah, that's all we're talking about there. There are a couple things. There's going to be one or two things that we're going to see that are a little bit different with vectors. We'll take a look at that on the next slide, which we jump over to Mr. Bean's notes. Bean and Gene. Yes, we have a mashup of Bean and Gene today. Some vector basics, things that, again, probably not, I've already said them. Vectors have a magnitude or a length and a direction. Vectors can be represented by directed line segments, so a line with an arrow on it. Vectors are equal if they have the same direction and magnitude. So the thought process there is, and this is a behind the scenes difference that we don't really need to worry about, but a vector, the starting point doesn't matter. So if I draw two lines that are as identical as I can do by hand, and I didn't do that bad, if those directed lines are the same length and going in exactly the same direction, they are the same vector, even if they are in different places. A way of sort of kind of visualizing that, I did graph the vector equation from the previous page. So it was, hopefully I didn't make any mistakes. Yeah, t cosine t plus t sine t. That equation, if I was saying parametric equations, this would be our only shape. This would be our graph. But because vectors, they're the same no matter where they are, any one of these graphs could be that vector equation. And all I did was add random numbers on the ends of them. Plus 6 minus 2, minus 3 plus 2. So that's like an underlying thing about vectors. Vectors don't have any position. They're just, a change from wherever you started from. So that graph could really be anywhere there. But we generally, just for simplicity, the red one is the one we would generally be thinking of. Why add extra numbers that overcomplicate stuff? So that's like an under the hood difference between vectors, but it's not something we'll ever actually have to deal with. So yeah, go back. Cool. All right. So yeah, this one's important, and this is definitely something extra about vectors that we wouldn't necessarily have had with parametric equations. Magnitude is designated by two bars around whatever your vector is. Gene uses R a lot. It looks like Mr. Bean uses V, but whatever you're using for your variable to represent your vector, this is magnitude. And magnitude is the length of the line. So it really just ends up being either the distance formula or the Pythagorean theorem. So if that's part of the reason why we really like to keep our vectors oriented at the origin, magnitude can be found by basically just taking the square root of x squared plus y squared. If you're starting at the origin, you don't need the x minus x1s or the y minus y1s. And really that just comes from the Pythagorean theorem. If that's going to be your x value and that's going to be your y value, a squared plus b squared equals c squared. The magnitude, which is the length of your vector, is just the Pythagorean theorem. We refer to those x's and y's as horizontal and vertical components, and we've seen this on the slide from before. All right. So a very simple example, really just sort of review. Find the component form and the magnitude of the vector that has an initial point of 1, 2 and a terminal point of 5, 4. So really what we're trying to do is we're just trying to find out what the change is in x's from the initial point to the terminal point and the changes in y's. So to write that in component form, I would just take the terminal point and subtract the initial point. So it would be 5 minus 1. And we went from 2 to 4, so we went 4 minus 2. And then that would, of course, equal 4, 2. really, we just did rise over run, guys. That's all we did there. How much did I have to go? And I shouldn't say we did rise over run. We did run first and then rise. It's just a different way of showing it. How much did we have to move to go from 1 to 5? That's positive 4. How much did we have to go to move from 2 to 4? We went positive 2. All we did there. And then those numbers are what we would use to find the magnitude of our vector. It's just the square root of x squared plus y squared, which is 16 plus 4, which is the square root of 20. Square root of 20, we saw this a little bit yesterday if you were working on that one problem in class. Remember how to simplify a square root? Look for perfect squares on the inside. What perfect square can I divide 20 by? Close. 4. 4, yeah. Yeah, it'll end up being a 2, but yeah, I'm thinking 4. I can divide 20 by 4. That's going to mean the square root of 4 is 2, and the leftover is 5. All the way back to Algebra 1 and also in Algebra 2. All right. It wasn't hard to differentiate parametric equations. You just did it by the components, and that's all we're going to do with vector value functions. So if your vector r of t has components f of t, g, and t, then r prime of t, the derivative of that function, is just f prime of t, comma g prime of t. And all of the rules that worked with regular derivatives that we learned back in chapter 2 and 3 work with vector value functions. A constant multiple in front of your vector, when you take its derivative, is just going to be something that you would multiply on the outside, which means you would multiply it against both f prime of t and g prime of t. Actually, don't know why Mr. Bean doesn't have that there, so maybe I'll add those in as they are simple to write. So cf prime of t, comma cg prime of t. So constant multiple does what you would expect. If I put a 2 in front of the problem, that just puts a 2 in front of everything. That's what that's saying. If you're trying to take the derivative of 2 vectors being added, you can take the individual derivatives and add them. Not as easy to write out, but basically this would have its own f and g. This would have its own f and g. I'd have to use different letters. You could take each individual f individually and then add your results. So you've got 2 vectors being added. You do what your instincts would tell you to do. Take all of the derivatives, add what needs to be added. Multiplication still needs to use the power rule. So you would have to, sorry, not the power rule, the product rule, same first letter. And this is the same product rule we've had since the beginning. You would have to multiply the derivative of the first times the second, and then the first times the derivative of the second. That being said, I'm not sure if we've actually learned how to multiply vectors, so I would be wondering to see whether there's actually an example where that comes into play. And then last but not least, the chain rule. I feel like this looks confusing when I looked at it the first time, but example number 2 is going to be an in-context example. But this is the chain rule written out. The chain rule looked exactly like this with just different letters. So we'll do an example of the chain rule and see how that works. All right, so we have 3 examples to go over. The first one is just the most basic thing. It's exactly what we were doing with parametric equations. If r of t equals this vector, then r prime of t just equals those individual derivatives as a vector. So we got to use the power rule 5 times. 2t squared becomes 4t. 4t becomes 4. 1 becomes 0. And then this ends going to end up being 9t squared minus 4. It works just the way you would want it to work. Take the derivative of each of those two things. They're both polynomials. So we have R of t in this next example. This is the chain rule example. We have R of t, and we need to find the derivative of R of 2t. So the way that we're going to do this is we are going to first find the derivative of t, and then we're just going to use the chain rule to get the derivative of R prime of 2t. So the derivative, more power rule, 3t squared, comma, 2. If I want to plug something in here different than t, I'm going to plug that 2t in everywhere where I saw t, but at the end, I have to multiply by the derivative of 2t. That's the chain rule. That's what the chain rule was back in chapter 3. So what I'm going to do is I'm going to plug in, instead of 3t squared, I've got 3 times 2t squared. And there's nothing to plug in here because it's just a 2. So in two steps for full clarity. I hate the way I have this written. I used the parentheses there because it was t squared. The squared should be on the outside. I am plugging in 2t where the t was, and that t was being squared, so that means 2t needs to be squared. So we have 4t squared times 3, which is 12t squared. And that 2 still stays a 2. And the derivative of 2t is just 2. We end up with 24t squared, comma 4. I almost wrote 2, but that is correct. I do think you could get the same result if you first plugged 2t in for all of your t's here and then took the regular derivative, but this way highlights the chain rule. So it might have been a little bit easier to have just done 2t to the third power, which would have been 2t to the third power, which would have been 8t cubed. Taking that derivative directly would have gotten the 24, 8 times 3. Plugging in 2t for this t would give us 2 times 2t, 4t. So that way highlights the chain rule, but there are also ways to just plug your thing into the original vector and then get the same result the same way. All right. And then last but not least, a little bit of particle motion, another little bit of a preview one. The path of a particle moving along the xy plane is given by the vector valued function f of t equals t squared, the vector t squared sine t. Find the slope of the path of the particle at t equals 3 pi over 4. So I'm actually going to go one step further of this. I'm going to find the slope and the tangent line. That way we can check it in Desmos. And I can show you a couple other things that you would have to do. So let's take a look. Same process as we were doing with dy. Actually, same process we were doing before, but we're doing it in vector form. So f prime of t would equal 2t. And what's the derivative of sine? Cosine. So now we want to find the f of 3 pi over 4, the f prime of 3 pi over 4. So we've got to do 2t, so 2 times 3 pi over 4. You could think of that as 6/4, or you can think of the 2/4 canceling to 1/2. Either way, you should get 3 pi over 2. And then we need to get cosine of 3 pi over 4. We have 3 rays inside our unit circle: pi over 6, pi over 4, pi over 3. Pi over 4 goes with the 45-degree angle, which is nice, because both sine and cosine of a 45-degree angle are the same. And what is that? Yep, square root of 2 over 2. So anytime you see a denominator of 4, you know you're working with square. Yeah, I wrote square root of pi there. I had pi in my head. You're working with square root of 2 over 2 in both instances. Okay. The reason that pi over 4 is the 45-degree angle is it sort of splits it. This is pi over 4. This is 2 pi over 4, which would be half pi. And then 3 pi over 4 is right here, a mirror image of that. So that point is going to be the same two numbers. What's going to be negative, the x or the y? The x, yeah. So negative square root of 2 over 2, square root of 2 over 2. That is supposed to be a parenthesis, but it doesn't look all that great. We want cosine of t, so we want the x or the y. We also want the x. Yep, so it's going to be negative square root of 2 over 2. So I want to find a tangent line to this function, which means that I need 2 things. I need a slope and I need a point. I don't have a slope in vector form, but the idea is this is my dx dt and this is my dy dt. So to do my dy dx, I'm going to take my dy dt first, negative square root of 2 over 2, and then put it over 3 pi over 2. I can definitely solve that using reciprocals. You can always cancel out, however, you can always also cancel out things that are in the same spots in the overall numerator and the overall denominator. So since this is divided by 2 and this is divided by 2, those 2's will cancel. If you don't see that, think of doing the reciprocal. This 2, when you bring it up here, is going to go up to the top and cancel out that 2. And that makes my numerator negative square root of 2 over 3 pi. So that is the slope at t equals 3 pi over 4. That's great for the question. If I want to do a tangent line, I also need a point. Well, that's what the original function is. The original function is how you find your point. So we have to find f of 3 pi over 4. Here's the one that gave me grief when I was trying to graph it and make sure I was correct. I've got to square 3 pi over 4, which means I have to square 3, square pi, and square 4. So that's actually 9 pi squared over 16. Plugging 3 pi 4 in for t squared. And then my x coordinate, or my y coordinate, sorry, is just sine t. My y component, I should say, is just sine of t. We said that this guy was the cosine of 3 pi over 4, so this must be the sine of 3 pi over 4. In a little over 2 weeks, when you're taking the AP test, anytime they ask you for a tangent line, the 2 things you need are a slope, which is a derivative of something, and then the point, which comes from that something. So my preferred form is y equals. My slope is negative 2, square root of 2 over 3 pi. X minus x1, so that's going to be x minus 9 pi squared over 16 plus y. So that's going to be plus square root of 2 over 2. I do have that somewhere in Desmos. Hopefully I can find it. I also have 45,000 tabs open. Maybe it's this one. Hey, look, there it is. So this is what t squared plus sine t looks like. I had t run from 0 to 10. Goes up and then slides down at the bottom. Here is the point that we're looking at when t equals, what was our t? Oh, 3 pi over 4, right? You know, that's the thing. When you know that t value, just looking at the line, you have no idea where you are on that line. But we figured out to be 9 pi squared over 16, comma, square root of 2 over 2. And then that horrendous looking tangent line with pi's and square root of 2's in it is in fact the tangent line. It touches it, very close to it. It's very close to it. The further you go away from it, the worse it is. Perfect time for the phone to ring. Pranac. No, he's not in school today. Yeah, he's at the Lego thing. There's something going on at the junior high with Legos, and he's there. Yep. Okay. All right. Bye.